Okay, let's start with hash indexes, LSM trees and SSTables, and then BTrees. So in this section, firstly we'll cover the hash indexes on a very high level. So you must be seeing it like take as a client, and then let's say we have a black box over here. So you can take up the black box as consider over here, let's say the load balancer, it can be the API gateway, then you can have API servers, right, which will handle your incoming request, and then eventually it would hit on the DB side. So you can see that on a high level, a developer from a developer perspective, the main goal is to get some data, say X, okay, and the DB would return that data. So then it retrieves X, and then again it goes from the black box, the API servers, and then they respond back to the client, right? So these DB choices you can take up as it can be SQL, it can be Redis, it can be Cassandra, it can be MongoDB, Bigtable, MySQL. You have a lot of options. So from a very high level, all these databases would do similar sort of thing, which is client wants to retrieve some data which is stored in these databases, and then it queries it, and then it responds back with the data, right? And if the data is not present, then respond back with like data is not present and that sort of stuff, right? But generally it's good to know that how these databases internally manages and stores the data, so that the choices that we are making as per our use cases for these databases, we can make some sort of optimal efficient choices, right? So we should know internally how these things work a little bit. Okay, so let's try to build from the basics. So you might be seeing like we write everything to a file. Okay, let's try to build it from very basic. So let's say take up a file, okay, and we can write all our contents, what we need to store, to a file. Let's try to take it and call as a append only file, or in short AOF. Try to treat it as a log, like you use logs in your application, right? Info logs, debug logs, so that everything eventually and might connect it to, let's say, Splunk or other systems, and eventually all the things gets printed out there, right? So to see all that stuff. Similarly, let's try to take it an append only file. So this will be immutable. That is, you cannot update a content once that is written, but you can keep appending all the new stuff. Okay. So for this, say I am dealing with key and values. Okay. So the data I am considering here is key and values. So let's say I have a key as name and the value is Rahul. Then the next key might be, let's say, hobby. Value is coding. Next key can be age. Value is 30. Company, Expedia, role, and so on, right? So if you keep on adding all of this to a file, okay, so all gets appended to a file. So after that, so it's written, that would be big O of one operation, because you go ahead and directly write it at the next possible available location. Okay. But if you want to look up for a certain key and its value, in such a case, cost becomes big O of n. Why? Because you are doing lookup and traversing throughout the file for every key and value and trying to match it with whatever key you are supplying. If it's the same key and if it's the same, then returning back that value. So that would be big O of n, because you have to sort of look up on all the keys present in this file, right, from start till the end. Okay, so let's try to think how we can optimize this. So to optimize this, we can build an index on the side. You might think of building an index on the side, sort of like a signpost, which can help the lookup give some sort of directions here and there, where to look for the key and where to not. Okay, to take us to our key value quickly. So this seems like a good option. But again, index would again be required as a separate structure to be created. So the downside is, on every write, we need to update the log, which is the append only file. And then now you also need to update your index as well. So that sort of becomes an overhead, right? For every write of a new key value. Makes sense, right? Upsides are that reads can become quicker. So generally a lot of systems and use cases which we have, they have reads much higher than the writes. So with using a separate structure, by building this index, so we can have some sort of upsides, but there are a lot of downsides. Another structure to maintain and manage, and then every write operation sort of becomes an overhead that we need to update that index. And again, that index can also become quite large as much as a file, because all the keys would need to be indexed, because here we sort of can't think of any condition or any sort of use cases how we can sort of like scenarios with how we can build our index in an optimal way. So let's see for that. So let's try to build on top of this. Like we have an index as a separate structure that we will maintain, and then we will have our actual AOF append only file or log file where we append the incoming data or the writes. Okay. So let's try to optimize somewhat towards the index side. So there firstly comes is hash index. So as I mentioned, we are already having this log file. Okay. So let's try to have this index as a hash map data structure. Okay. Let's use that and use it in memory. Okay. So the key which we will use in this hash map, we will keep it as the actual key, and the value we put for that key we will take as the byte offset in our append only file. Now what's that? So key makes sense, right? Whatever key is coming, we store it as the actual key in the hash map. But what's the byte offset here of our append only file? So let's see what's that. So let's say we have this file. Okay, so this is our file. So byte offset, by that we mean is for our key value pair, for our data which gets appended to the file for every write operation. Okay, so the byte offset means the starting index of that. For example, let's say we appended name Rahul, and then in the next line hobby coding, and then in the next line age 30. So the next line we are treating as another character of backslash n. So name Rahul starts at the byte offset of 0, and then we have 1 2 3 4 5 6 7 8 9 10, and then it hobby h, let's say for example, comes at the byte offset 11, and so on. So this way the size of our hash index we have reduced a little bit by just keeping the byte offset of the value, as the value can be um, quite as the value can be quite get large. So here let's say name Rahul, we are taking it as a whole value, right? So that's the value, and hobby coding is also value, and that might also be a little bit bigger, right? Let's say it's a sort of a structure as well, so that also we need to store it as a value in the hash map. So to optimize that and save somewhat on the space, byte offset would help a lot over here. So in my hash index now, the key becomes the name and the byte offset becomes the value. Okay. And then once we go reach the byte offset, we can traverse in the file, right, from that byte offset. We can traverse in the file from that byte offset to collect our value. Exactly. So this seems like a good approach, but for the use cases where keys are quite less and their updation is quite frequent. Now, as I mentioned above, right, that we have an in-memory hash map, right? And then we are appending all the values to the same file, right? So that's an in-memory hash map. So not to put too much overload, right, on the memory side of things. So this works well for a use case where keys are quite less and their updation is quite frequent. So that the keys that we have to maintain are quite less in number, that the distinct keys are quite less in number, right? Even though their updations keep on happening, that is fine. Which is, this is also the same thing, like larger number of writes or updations of same keys, but lesser number of distinct keys, as our hash index is stored in memory, right? So say my AOF contains 100 appends or write operations, but say distinct keys are 5 to 10 only. Something like this, like I'm just giving an example. So this works well for these cases. But still a downside with our log file, as that is append only. Now hash index is fine, but now again couple of downsides with our log file, is that is append only, and not like we are updating some already present value as the new write operations. Even though it's on the same key are coming, we are appending data to our append only file or log file. So even our distinct keys are less number. If same key updations are high number, our log file will soon become large enough. And that makes absolute sense. Like even if the distinct keys are lesser in number, so our hash index is fine, but our log file will grow and become very large enough. Now, somewhat a solution to this can be divide file into multiple segments. So our file becomes very large enough. Okay. So one solution that comes to our mind can be that what I'll do is I can keep some sort of a certain threshold. Okay. So let's say a size limit threshold. And as soon as my current file grows from that threshold, what I'll do is I'll divide my file into multiple segment files. Okay. And we'll keep doing this process once those further divided segment files would further reach their size limit thresholds. Okay. So someone, and like we might say, why we are complicating things to make files go into their get divided into multiple file segments after a certain size limit threshold, and keep recursively doing this process, breaking it into multiple and multiple file segments, and then eventually we have to manage all those segments, etc., etc., all that sort of stuff. Why not like keep data appending to just one log file? Why not just do that? That seems like an easier approach. And as we have lesser distinct keys, we saw hash index also quite works well, but that's not the case. Why? Because it's very hard to maintain files as they grow larger and larger in size. Like it's very hard to maintain and operate with files running in, let's say, GBs and TBs. Like some files say 3 TB in size, right? Very hard to maintain and operate on that, right? These such large files. That is why these sort of processes help to set some sort of certain threshold and keep breaking them into multiple file segments, which are easier to maintain, manage, and operate, and all that sort of stuff. So, how do we do that? Okay, we set the limit, that part is done. Okay, further processes comes into play as well, okay, which can further optimize some things and save us a lot of storage space. One such is our compaction and merging. So for example, let's say currently I have this one file segment. Let's say take this one file segment, okay, which has key value pairs. Okay, so let's say we have name Rahul, hobby coding, age 30. Again, a write operation came for hobby workout, then name user X, and then hobby running. As these are append only files, so they don't update the existing key, they just keep appending with the incoming values. Okay, so one process is compaction. What compaction does is compaction takes up the unique keys, okay, which are name, hobby, and age. So if you see right, name is present over here, hobby is present over here, and then over here, and age is present over here. Okay. Okay, so this is present. So what compaction does is it takes out the distinct keys and picks up the most recent value and fill that up. Value is the most recent one for each distinct key within the same file segment. Okay, so within the same file segment it would do that, and basically all the earlier versions of this value gets dropped. Okay, so if you see at the end, first we got name Rahul, and then we again got name user X, right? So it picked user X. Then you can see hobby got coding, then hobby came out to be workout, then hobby came out to be running, right? So it picked running, and then age, just one write operation came and got appended for age, nothing else, right? So if you see here, so directly age gets the most recent value and the only value as 30. So that's the process of compaction. Now this can save us a lot of space, as we saw our use case was that we will get, for the same keys will get a lot of update requests, right? So the distinct keys would be lesser in number, but a lot of operations get appended on that file. So this saves a lot of space over here. Saves a lot of space by removing the older versions and sort of key duplicates, right? So our use case was of same key being updated very large number of times. So compaction is, it shrinks to distinct key size within that log file segment, as I just recently explained. Okay. For example, as I just mentioned above as well, let's say total we got 100 key updates, but distinct are only 10. So compaction, it will only keep bring the size down from 100 keys to 10 key size with their most recent values. Now, as I mentioned, we break the file as once it crosses the size limit threshold into multiple log file segments. So we will have multiple log file segments, similar keys with same updated values present. So merging also helps a lot. Now it can be that our file gets broken down into multiple file segments, log file segments, and then on the same key that was present in an earlier file before getting divided now update requests come on the same key in the newer file segment as well, right? So similar keys with same updated values, with some with some updated values present. So what we can do is, here merging helps a lot. So this overall process is basically compaction plus merging. For example, let's say we have this LF1 and LF2. By that I mean log file segment 1 and log file segment 2. Okay. So for example, I had there in the, like it grew larger than the size threshold, the log file segment 1, and it divided it into log file segment 2, and new operations, new rides also kept on getting appended with existing or fresh key value pairs data. Let's say we had name Rahul, hobby coding, age 30, hobby workout, name user X, hobby running, and so and so. And then in the log file segment 2, we had name John, hobby TV shows, name Jacob, pet dog, right? So we can sort of do is compaction. So what will compaction do is, for my LF1, my compaction will keep this value, name as user X, makes sense, and then hobby as running, and then age as 30. And then in the log file segment 2, pet as dog, then my name as Jacob, and hobby as TV shows, right? And then comes the process of merging. So what will merging do is, it will also merge both the log file segments over here. So to overwrite, so to pick again the, for the same key, the latest or the most recent value from the most recently updated log file segment. So it picks the most recent value from the most recent log file segment as well. So now we have name as user X over here and name as Jacob over here. So and then my name is John as well. So this should be Jacob and not John. Got it. So this would be Jacob. Um, right. Hobby will be TV shows. Makes sense. And then age is 30 and then pet is dog. So this makes sense, right? Now each log file segment has its own hash index which is in memory, right? So in the very starting of hash index, we saw that we have a file and then there was a hash index of that file and it was in memory. Similarly over here, as we are dividing files into log file segments and multiple log file segments, once they reach their certain threshold and we keep doing compaction and merging, right? So here each log file segment has its own hash index, okay? And all of these hash index are in memory. So what if a key lookup comes up, right? So what we can do is we have these log file segments from the most recent one to the older ones. So what we'll do is we'll do lookup one by one on the hash indexes of each of these log file segments, right? So we check key in most recent log file segment, okay? If it's found, then we are good to go. If not found, right? If found, good to go. If not found, then we go and check one previous log file segment. And then we keep doing the same process till the key is found or we declare it as not found. So one drawback that comes out of this is in case of key which is not present, we have to check all log file segments, which is the most recent one till the oldest one, right? Even though compaction and merging keeps the log file segments lower in number, still for a key on a worst case that is not present at all, these are sort of a wasted lookups from the most recent log file segment to the oldest one. Basically all the log file segments, we have to go through that, right? Now what if, so that's a drawback, right? Now what if a key needs to be removed? So for this, it takes up a slightly different approach. We append our latest currently running log file segment and we append, right, a special value called as a tombstone value for the key which needs to be removed. As and why do we do that rather than removing it? As we just discussed from the very beginning, these log file segments are immutable and these are append only files. The special tombstone marker tells to discard all values to this same key in all previous log file segment during compaction and merging. So what this tombstone marker will do, this will tell during our compaction and merging process, wherever it's found for a certain key, to drop all the values which exist in all the log file segments for this key. Now we saw that hash index, we saw that it's for all the log file segments, all the hash index were in memory. As it's in memory, and each log file segment has its own hash index, so we can rebuild it from all the kv, so key values that are present in its log file segment for its specific hash index in case of crashes. So what if a crash comes in, so and all these, like couple of these hash indexes of these log file segments get deleted or something. So what we can do is we can rebuild it from the key values that are appended in our log file segment, and we can rebuild or reconstruct our hash index again in memory once it recovers back, right? So what are limitations of this overall approach? So this approach is good enough for certain use cases but has couple of limitations, as we saw above as well, lot of drawbacks and couple of some limitations, due to which we will further build upon to recover, to work upon these limitations. And this is where our um, SSTables and LSM trees and our BTrees comes into picture. But for now, what are these limitations? That all hash index are in memory for all the log file segments as we discussed above. So even though our use case was that a lot of operations coming on the same key and the distinct keys are a bit lesser in number, but still there is overload on the memory and we might go out of memory. Range queries are not possible. For example, get me all the keys plus values, its values, do the lookups for a range of key, say key ABF till key ABZ. Okay. Or for example, let's say I have to do from, let's say, apples to oranges. So all the keys, right, which lie between these, get all the keys. So this requires sort of a brute force approach only, like all keys needs to be looked up into all log file segments. So these are not that efficient to see whatever keys lies in that range.